All right, so we have here for the circuit shown below here. We have a source voltage of 120 volts. That's RMS, and it's at 60 hertz. Over here, and this value of resistance, it is 20 ohm, and we have an inductor here of inductance 0.04 Henry, and you're told that there's a delay angle of 45 degrees Celsius. To also determine the expression for the current, right? That's for this current, the current that will be flowing through your SCR, and the load you have here, the RL load. And it then asks you to determine the average current. Right, so that's the question. I want you to start working it. How is it going? Yeah. So be sure you don't have to use that formula. That's the format you want to get it in. So you have to determine what the peak voltage is, right? Um, you're going to have to determine what your thought is, right? And you're going to have to determine what your theta is equal to.
Download the new Scotia app for the faster no-time bank wherever, whenever. Create, control, and transfer funds or pay bills quicker with just a few taps and a swipe. Plus, for serious.
Sir,
Yeah. How is it?
I jumped. I don't know what's happening.
Huh?
Jump. Was lost a while ago. I don't know what's happening. You hear
Oh,
me?
yeah, I hear you, but you weren't coming across clearly a while ago. I'm hearing you now. Uh-huh. How is it going?
My computer actually failed. I don't know what's happening. My computer failed a while ago.
Feel.
I had to restart.
Oh, you just okay. So you just come back in. Okay.
Yeah,
All
yeah.
right. Okay. All right. So that's the question. I'm giving you a little time to look at.
What is the question, sir?
You're not seeing it?
No, I'm just seeing a formula.
Oh, let me go back. That's the question.
Oh, I'm gonna write it down.
Sir, we should work in Radian.
Yes, it's best if you work in Radiant. All right, how far are you?
Um, side.
All right, so you know that your you have to first get your Z. You know what Z is, right? So you have to work out your Z. All right, let me just put it here. So that would be the square root of your R square plus your XL square. So here Z, and my pen not writing. Here Z here is equal to square root of just and that would be r square plus your xl square, right? And your r square substitute. What was r? Let's go back and now look at r. That's on 20 square. So 20 square plus xl. That would be 2 pi times the frequency. So the frequency here is 60 hertz. 9 to pi times 60. And the inductance they're told here is 104 Henry.
Point zero four.
Alright. Can work that out. And you know what your tau is equal to. Your tau here is the what's your tau?
It's going to be
L over R, right?
Yes, sir.
So that's your 104 over your R. What was R again? 20. If you have worked out Z already?
Yes, sir. It's 20.
Yes, sir.
What is it? 20 or Z? The impedance.
25. 25.047.
24.0.
25.047.
04. All right, let's just have it at 0.5 ohm. And the tau is that will be 4 over 100, 20.8.
Oh, sir. 2 times 10 to the minus 3.
For tau,
Yes, sir.
Yeah, it's
0.02, sir. 0.002.
yes.
0.002, sir.
Yeah. All right. So now you have those values and start putting it somewhat in a form. Right? And what is the peak VM? Right? You're told that what was it? That you
120
have
VRMS.
120 RMS. So the peak is going to be what? 120 times root 2. What's that equal to?
$169.
169.70, sir.
0.7. All right, so we have those values that we can substitute. All right, can also find out what
Is it?
the state that is. What is phi?
Sir,
Uh-huh.
30, sir.
How much?
No, pi over 6.
Pi by 6.
Yes, sir.
How did you get it? How did you get pi over 6?
sir,
Yes.
I'm not getting 25 for the impedance. I'm getting 20.
20. Oh, I don't
Yes,
know.
sir.
I don't know who told me 25.
So it's 25.
Yeah? 25.
25, sir.
Hold on. 25 or I'm hearing all kind of answer.
Sir, it's 25.
Check it again, Conroy.
It's 20 squared plus 2
25,
pi.
sir. 0.04.
Yeah, it has to be a little bigger than 20.
Well, it has some decimal points behind it, but
Check it again.
25.0, sir.
Yes, sir.
Oh.
25.
That's 0.4. 0.404 henries or is millihenries.
Henry.
Henry.
Henry. Okay. All right. I have millihenries. All right.
Okay. All right. I wanted to convert this delay angle for me into radians. So when I have alpha equal 45, what is that in radian? That's just 45 over 185. Right?
You get a pi over.
Huh?
I get 1/4 pi.
1/4 pi?
Yes, sir.
Right. So that's just, simplify that. That's just 0.25 pi radian. All right. So we have all these things that we can substitute now. Alright, so we can go ahead and start our substitution.
So we can work on theta.
Theta?
Yeah.
5/6.
How did you get theta?
It should
Oh,
be
my bad, sir. Not my apologies.
it should be tan inverse ta.
Yeah. Your
It's actually
theta,
5/4. I was saying wrong thing, sir. My bad.
your theta tan inverse of omega L over R, right? Now when you substitute that, what do you get?
So I wanted to know
37.0156.
okay. So it's we could have it in that gradient.
0.6460 in rad.
And 0.64 radian. All right, good. So now you can start putting this in the format that they asked us for. All right, so your in terms of omega and t, Vz, we have our 25 here over 25.05, that is. I may need more space for this. Let me put this on the next page. Need a page, all right. So I, in terms of omega t, your Vz, that's equal to Pm 169.71, and over your Z, which is equal to 25.05. right? And that goes into sine omega t minus theta. And your theta was found to be equal to that's 0.064. And now you're supposed to add sine of theta. And you found theta to be equal to that's 0.64. But here is e to the minus omega t over omega tau. And of course, your tau is equal to 0.002. So if I make that substitution, this divided by and the tau did I write something around here? The omega tau over tau. All right, so we can now simplify what we have here. All right. Please proceed with simplifying this. Okay. All right, so just substitute values there. How is it coming out? I think right here, I think there's an error right up here. This should be, let me just fix this. The error is from up here, top. I really should have written this this out in a format where we have omega t minus theta minus sine of alpha minus theta. That's the way we should have actually have this written out.
So, sir, which form?
I think I wrote it out incorrectly. Now that I look at it, I think I wrote it out incorrectly. So I'll have to go and fix and see if I can fix this here. Alright, so this omega t minus alpha, but this should be alpha. Need alpha here. Alpha. There's no alpha. Don't see it in that. No alpha in here. Alpha. Greek letters. Alpha. Alright. So alpha. Right. So this should be alpha minus theta. And up here, it may come across. It should now be e to the alpha minus omega t. Where's my Greek? Right, so e to the alpha minus omega t divided by omega tau. Alright, let's see, I have it right. Right, so alpha minus theta, yes. Alright. So, sorry about that little mistake, so let us fix that part up. Alright. Formulation. Alright, let's put it right there so that we can see this thing clearly. Put it right, not erasing it. Not sure why, because I saved it a while. Alright, I'm going to have to remove this one and be all over right here again. All right. All right. Our VM 69.71 over your Z here, your Z of 25.05, and this should be sine of omega t minus theta, and we work out theta to the bit equal to 0.64. Oh, and there's still, oh, I don't want to, let me do the, oh man, this here should be minus, minus, minus. Oh man, accidentally removed it. All right, so what's our alpha here? What's our alpha?
0.25.
That's a delay angle. They told us. That was, and you worked it out a while ago, 0.25. And the theta, 0.64.
Sorry, 0.25.
Huh? So wait, 0.25 pi, work out that in radians. Sorry, work this out. So what do you get? Multiply that by pi, what you get?
0.785.
All right, so e to the minus alpha. Sorry, not minus. I don't know why I'm always saying minus here. E to the alpha minus omega t divided by this was at 0.002 what was it again? And multiply omega times tau, what did we get? No, we didn't multiply. All right, you have to multiply it now. 0.002 times your omega here. You didn't work that out. All right. 2 pi f. Thought we worked that out a while ago. No, I don't know. See. How much is it?
1.3 times 10 to the minus 3.
For your omega 1.3 times 10 to the minus 3. All right, so
that's
huh?
the total.
Oh, 1.3.
Yes, sir.
So
So you can get the total for the not the total.
I think you're saying that omega equal 2 pi f, right? So 2 pi times 60 to 120 pi, and he sent what was this? Huh? Right, so therefore your omega tau is equal to 120 pi multiplied by 0.002, right? And what's that equal to?
It's over 20. 6 over 20.
Yeah, work that out as a fraction, you get 25.
0.
Yeah.
Yeah, what did you want to be?
0.75. W? The omega, you mean omega? It's not W, we use omega. Use omega. Omega is 2 pi f. So the frequency you're told is 60. So that's 160 pi. And then we need omega tau in the expression. So work out omega tau. This is 120 pi multiplied by tau. Found tau to be equal to 0.002. And we multiply that, we get 0.75 radians. So we can substitute. So you can work that out. Give you some time. Hope you don't make any mistake. Give you a few minutes. finish. All right. And so maybe you can write this over and tidy it up as you go along. All right, so this part, I can just have this as e to the minus 0.75. Still multiply this by e to the that would be what, alpha minus omega t. All right, so to make this better.
Sir,
Huh?
should
I made a mistake.
I'm just checking.
Yeah.
E to the negative 1 over 0.75 instead of 0.75.
E to the what?
1 over 0.75.
Yeah, you can have it like that. It don't really matter, right? It don't really matter, right? It's just if you have x to the the half, x to the half, right? Right, we can write this. This is equivalent to you writing x to the What do you get?
What was it?
You're supposed to be simplifying this. Now, this way, by writing it this way, you just be able to get your constant right here. And here, a constant.
Sir, I don't know if you can hear me.
You understand what I'm doing? I just break the top up. That's what I did. So you have like x to a times x to b, same as having x a b. That's what I did here. That's how I broke up the top part. That's what I did. So I have the two components. So this component e to the minus e to the alpha minus omega t. This is it. And I have e to the minus 7. Yeah.
Yes, sir.
So that's basically what I did. Just break that up. So what you get? Remember, your calculator should be in radian.
You want the yeah, you want the entire expression?
Oh, you have the entire expression?
Yes, sir.
What you have?
6.77 bracket sine omega t minus 0.64 minus 0.66 e to the 0.
Minus what?
0.066 e to the 0.785 minus omega t.
Then when you multiply that e to the minus whatever by it, what you get?
Repeat that, sir.
When you multiply, remember this part you can work out this.
Yes, sir.
All of this you can work out. What you get?
So yeah, I get 0.66.
Yeah, 0.66?
Point.
0.066.
Yes, sir.
And multiply it by this, what you get?
I got 0.45.
Huh?
0.4.
0.45.
Yes, sir.
All right. All right. All right. I think we can simplify this in a bit more. Because we should have simplified this a little more. All right. This. Let us change this. In this way, it would simplify better. I think that's all right. Because we know the delay angle here, I could just keep this as the alpha over 0.75. We know alpha. What was our alpha? What I'm doing, let me write it here so that you see clearly. Alpha minus omega t we can write this as e to the, just separating this part because we know what the alpha is, so I just keep the next part by itself. So I'm going to write this as this is 0.75. That's right. 0.75. All right, so we just break this up. So this comes to alpha. We know what alpha is, over 0.75. Right, so that's one part. E to the minus omega t here over 0.75. So just split this up right here, like that. So your alpha, you just work out your alpha just now. Remember what you got, alpha 0.25 radian. Multiply that by pi, what you get? 0.25 multiplied by pi, that's equal to what?
7.5.
How much?
0.78.
0.78. It is 0.78, and that's over 0.75. Right, so e to the minus omega t over 0.75. Right, so that's what you substitute up here. So your e to the right, so I want to make it as simple as possible. Right, so you can work out this part now. All of this part, you can get a whole number, and we have it just in terms of omega and t. A while ago we were, I think I made a mistake. Right, I left the alpha in it, and we know it. So if I continued like that, it would make it very untidy. I think I made a mistake here, but anyhow, we fix it. So this is how we break it up. All right, so what do you get now? Hmm?
0.4.
This part is 0.4, and multiply it by this, what you get.
Okay. I get 2.79.
2 point what?
79.
2.79. All right, and work with that. And this, when you multiply it, work this. So what was it again? It was 160. Sorry, 169.7 over 25. What's that?
6.7.
So that's 6.7 sine. So this would be omega t minus 0.64 minus, and you told me again 2 point what?
2.79.
2.79 plus e to the minus omega t over 0.75. So this looks more like it. Sorry about the error. I was making an error earlier on. Alright, so that's what it simplifies down to. And of course, amperes. Question asks us for the average current. average current. All right, so how you take average? Average. How are you going to get the average of this? That's a question now. Let me see, can I take this? No, I just wanted to carry that piece over there, but let me get another piece of the board here. Yep, so that's it. So your I omega t is equal to that. How do you find the average of it? So for part B, we need the average. Average current. Remember how the sine wave looks? The rectified output. Right, for this output, remember we have what's going in at the input. We have our sine wave, and at the output we have a controlled output, right? Semi-controlled rather. Let's say we have this firing angle right at this point. Right, so this is where you have your alpha here. So to get the average, right, over the period, right? So up here we have 2 pi, here would be pi. So the average over one cycle, that would be 0 Vm. So it should be Vm sine omega t. So the average here, output, that is average of Vm sine omega t, and of course we integrate respect to omega t, and this would be over 2 pi, right? Over 2 pi. That's where we are taking this average. Our limit is going to be from alpha up to where it makes sense we sum. Oh, here is 0. If we sum beyond pi, that's 0. So we sum from alpha up to pi. Right? That is for when we consider the resistive load, but this is not resistive load we have here. Okay, so that's what the idea is pretty much the same. So we have this current, so how are we going to find the average? Right, so we are going to have to do the same here. So let me just I average. So that would be equal to all right. So we go up to 2 pi, we divide by 2 pi, but what would we put in as our limit?
Same as
Huh?
triangle and
All right. Let's up to where it's going to go back to 0. We can use beta here up to when it goes back to 0. When we're looking at the somebody is saying something. Who is saying something here? Uh, 2 pi. Joseph. 0 to 2 pi. No. It can be 0 to 2 pi. Alright, let me go back. Alright, so it would be, if you recall what it looks like when we have the inductor in it, you observe that negative spike there, right? It cuts off, right? So we want to find that that extinction angle. So it would be up to that point. So what is the extinction angle? You remember what I'm talking about? Right, this is what I do here. This is for when you have a pure resistor. Remember when we were looking at this initially, and oh man, let me, right? This, you remember it come down like that. Something like, sorry. Extend a bit and come up. You remember, right? And we reasoned out how this part came in the picture. It was because of the inductor. Are you following me?
yes, sir.
Right. So it made this have a slightly conduct as for a slightly longer time. Let me check out this part so that I can give you a better picture. Right. So it will come up a little longer, something like that. Little spike. So I want to find the extinction angle. Right? What is the beta? I remember extinction angle, the point at which it goes to 0. This is just a very narrow spike that you observe. So we can consider our beta here, and for our average. So what's beta? What's the extinction angle? We know what our alpha is. Uh, so you can find your extinction angle. Are you with me?
Yes, sir.
All right, so based on that, use the graph. Where's the graph? The graph here. Okay. All right. Use a graph and determine what your angle is going to be equal to here, that extinction angle. So when you have forgotten that already. So when you have 45 degrees as a triangle, what is your extinction angle? And there's a graph, you can work that out. Right, so it is 0.25 times pi. Nothing. Remember, I gave you a method whereby if you have this and this expression here, and you want to find what your extinction angle is for this, then you set this equal to 0 and use some numerical method. But then I showed you a graphical technique, so you didn't have to go that route. Right, so it's alpha. So after you get that angle, you'll come here on the graph and find out what beta is equal to. What do you get? this. Hmm? Who is speaking? Why don't turn on mic, Joseph? 220. Alright, how much radian that is? Alright. Alright, so we can estimate it when we have 45 and what beta is equal to. So you come look at it here, see what 45, you have 45. You have forgotten this already? It's 45. And you then come down. You can probably get it better than I am doing here. Probably don't line this up properly. Who is speaking? 11:09 radian. Everybody agree with Joseph's? We use that? Yeah, it's about, yeah, it's within the range. 45. Try doing it lean. All right, we can take that to 20. So we have that range that we can work with. All right, so we're going to now integrate. It's going to be 1/2 pi. And we say we're going from, what was that? Alpha. I think you said 0.785. And we
Yes,
go up to 3 point, how much this work out to be?
3.84.
3.1? 3.84. And the next thing we must write here. So, all right, 6.7. Sine. I get 4, not 4. 6.7 sine. Omega t minus 0.64. All right, and then minus 2.79. X minus omega t over, what is this? 0.75. Right, of course you're integrating all of this. All right, what you get? You can work it long way, right? You should be able to integrate at this stage. Or the exam, you are allowed this on your calculator. You can just put the values in. Right, so you can put that in a calculator. Tell me what you get. Conroy, are you still here? I don't hear Conroy.
Yes, sir.
Oh, I thought your computer was giving some problem. You're working it?
Yes, sir. Yes, sir.
All right.
Sir, when me I put it in the calculator, I get 2.027.
Sorry, right. How much you get? Oh, yeah. So about that. 2 point something? 2.0 what? Hold on. I don't. Look at. Speak again.
2.027.
2.027. All right. That's not bad. That's not bad. 2.0. Help me. Anybody get any other answer? Mm, but who said something here? So no. Yeah, 2.01, 2.017. All right. All right. Right, that's about it. So, all right, can you find the RMS now? Suppose you ask, I'm just adding a next part to it. What's the RMS? Hmm? You want to find the RMS. How would you find it? Very simple, square. Square this part of the function. Still divide by a 2 pi. Just square it, divide by a 2 pi, same limit, integrate with respect to omega t. What you get?
Patricia,
Huh?
what was the formula?
The formula? No, you should know it. What we mean by RMS, right? You don't square. You're going to square this part of a function, right? This part, square that. Everything else remains as is, right? So you take this part, square it, integrate it with it between these limits, and divide by the 2 pi. That's the root mean square. Sorry, and then take the square root. You need the square root as well. So square root of all of that, right? So you're going to take the square root of all of this. Square root all of this. Let me write it out so that you can follow what I'm saying. Square root of all of that. That's a root mean square. When you do that, what is the RMS? Don't leave out the square. There's a square there. Here.
I got
Huh?
3.25.
All right. Is who type something? Yes, is Joseph 3.24. All right, about the same thing. All right, so good. Common mistake students make is take this 2.017 and multiply and divide it by root 2. I should rework another question. I should go to the tutorial. To the start a lesson. All right. I think we probably can work this one in another class. Sorry, you can probably look at it. Look at it now. Can you work it? Let me.
Yes.
You can. Just make a little space here, so for this. All right, so we have an SCR that is connected in series with a 0.5 Henry inductor and a 20 ohm resistor. We have a 100 volt DC source that's applied to the circuit, and the latching current of the SCR is 4 milliampere. We have to find the minimum width of the gate trigger pulse required to properly turn this SCR on. So you have to find out now what is the width. You understand? There's a pulse that is going to trigger the SCR. What is the width? And of course, width here, let me draw this bigger for a little more emphasis. We say a narrow pulse. So by width, we mean the duration of the pulse, right? That's basically this T we need to find out. What is the duration of this pulse? Right? So how we approach that and think about it. It's very simple. All right, let me start here. We can write a generalized expression for the current that will be going through that. Let's say it is I at any given time, right? So the source voltage V over R, that is current. And of course, we know how that is going to decay, right? Or increase rather. E to the minus, what would that be? T over R L, right? All right, so can make the substitution, right? So that is this is giving you that's a latching current, right? So that's when the SCR is going to turn on. So I could basically write that's the latching current, right? And so make the substitution, right? So that's the current that the minimum current that must flow, right? That's the latching current, right? So I say IL for latching, right? So you can make a substitution and work it out. And what did it tell us that the latching is current? All right, 4 milliampere. Right? You understand why it's latching current? Because we're finding the minimum width of the gate trigger that is required to turn it on. Right? So this expression that we have, it must be the latching current, right? The minimum current that will flow when the device turn on, right? That's the latching current, right? So that current that is flowing when it turns on, that's the latching current. So we can now substitute the values. We know what our latching current is, but it tells us a while ago 4 milliamperes. So we can substitute that 4 milliamperes and V and S. So we tell our V, the source voltage Vs 100, and we need R. What is R here again? R is 20 ohms. So 100 over 20, and this is into 1 minus e to the minus t, and we have r, so r is at 20, and the L, what was the L? Inductor here is 0.5, so 20 over 0.5. Work that out, what I get. So find t. You must can find t. Just make t the subject of the formula, right? And that t will give us the minimum width, right? This is what we're talking about, that pulse. Work it out and let me know what I get. Finish. You're just making this t the subject of a formula. Still there?
Yes, sir.
What answer you get? Joseph, you don't get any answer yet? 20 microsecond. Yeah, 20 microsecond. Everybody get that? Who types in? Wait, what happened here, sir? Whoa, when I switch here, I lost what I was working. Oh boy, I apologize for that. I think I wrote it on the screen already. 20
Sir,
microseconds.
just press Control Z.
Um, no, it's not. It's right. So what I was working out here, it seems to have disappeared somehow. Disappeared. Yep. When I moved, I didn't remember to keep it, but anyway, I think I wrote the answer there already, and it's just for you to put in the answer. Make T the subject of the formula. All right, let me just come back, please. I think I can start.